Welcome back, everyone. Today, we're going to explore a key part of the machine learning process model development and offline evaluation. This is where we take all the groundwork laid in data preparation and feature engineering and turn it into something that actually makes predictions. Let's walk through the process and break it down step by step. First things first, model development is not a one time thing, it's an iterative process. What do I mean by that? Well, it's a continuous loop of experimenting, evaluating, and refining your model. You don't just build a model and call it done. You tweak it, test it, and keep improving it until it gets better and better. One of the most important steps in this process is model selection. Choosing the right model is crucial. It's not just about picking the model with the best accuracy on paper. There are trade offs to consider. Think about things like complexity, interpretability, computational cost, and future improvements. For example, let's say you're working on text classification. You could choose from a range of models, maybe naive Bayes, logistic regression, RNNs, or even transformers. Each has its own strengths and weaknesses, and it's your job to pick the one that fits the task best. Once you've selected the model, it's time to train it. This is where the heavy lifting happens. Training involves using your data to teach the model how to make predictions. And it's not just one pass, it's multiple passes over the data, each time refining the model to minimize the error. During this phase, you'll also be tuning hyperparameters, things like learning rate or batch size, to make sure the model learns in the most efficient way possible. Another cool thing that's become more common is using pre-trained models or embeddings. Think of it as a shortcut. Rather than starting from scratch, you leverage a model that's already learned some general features and adapt it to your task. It saves time and often boosts performance. Sometimes the best way to get a better model is to combine multiple models. This is where ensemble learning comes in. By combining the predictions of several models, you often get a more robust, reliable result. It's kind of like having a group of experts. The more voices you have, the more likely you are to get the right answer. But just like in real life, this can come at a cost. Ensemble models can be slower and harder to interpret than a single model. Now, imagine you're working on a large project with tons of experimentation. How do you keep track of what's working and what's not? This is where experiment tracking and versioning come into play. You need to log everything: the training parameters, the metrics, even the performance on different data splits. This is key for reproducibility and debugging. It allows you to compare different experiments and understand how small changes in the model or data affect performance. Without this, it's easy to lose track of what's working and why. And if your dataset is massive, distributed training is the way to go. Instead of training the model on one machine, you can spread the workload across multiple machines. This speeds up the process significantly. There are two common techniques: data parallelism, where the data is split across machines, and model parallelism, where the model itself is split. It's like having multiple workers in a factory, each working on a different part of the process to get things done faster. For those of you looking to automate parts of the process, AutoML is a game changer. It automates tasks like hyperparameter tuning or even searching for the best model architecture. Instead of manually testing different hyperparameters, AutoML can automatically search for the optimal values. It's like having a personal assistant for your machine learning workflow. One example is Neural Architecture Search, NAS, which automates the design of the model architecture itself. It's like letting an AI figure out the best structure for your neural network. Let's zoom out for a second. When you're adopting machine learning in an organization, you're going to follow a progression. There are four phases to consider. Phase 1: start with simple heuristics or rules. Phase 2: use basic, off the shelf models and focus on data quality. Phase 3: refine your model with more advanced techniques. Phase 4: automate the entire process of developing and deploying models. You will need to adjust your strategy based on which phase your organization is in, but the goal is always the same: build better, smarter models over time. Before you ever deploy a model into production, you need to test it. This is where offline evaluation comes in. You want to check the performance of your model without risking any real world consequences. And here's the key: Compare your model's performance to a baseline. For example, how does your model compare to random predictions or even simple heuristics? This gives you a benchmark to know if your model is actually improving things. There are several ways to evaluate your model beyond just looking at accuracy. Let's look at a few. Perturbation tests. This tests how your model performs on noisy data to ensure robustness. Directional expectation tests. You want to make sure that when the inputs change, the model's outputs change in the expected direction. For example, if you're predicting house prices, a larger house should have a higher predicted price. Confidence measurement. This is about understanding when your model is unsure. Knowing when the model lacks confidence is crucial for trustworthiness. Calibration. Your model's predicted probabilities should match real-world frequencies. For example, if your model predicts a 70% chance of rain, it should rain 70% of the time. Slice-based evaluation. This looks at how your model performs across different groups in your data, helping you spot biases that could affect certain segments. Why is all of this so important? Well, model development and offline evaluation ensure that your model is reliable, accurate, and fair before it's deployed. Without this step, you might run into issues once the model hits production, affecting users or business outcomes. Offline evaluation also allows you to make informed decisions about which model is best suited for a given application. It's all about avoiding surprises and ensuring the model works well across different conditions. At the end of the day, model development is an iterative process that requires constant testing and refining. And offline evaluation, it's absolutely crucial for making sure your model works as expected and is ready for deployment. If you found this video useful, make sure to hit like and subscribe for more insights on machine learning. And remember, building a model is just the beginning. Ensuring it performs well through offline evaluation is what will make your ML systems truly effective. Catch you in the next one.